Alright, so let's deal with gas law. Let's deal with gas law. Before then, let's consider something please. Kinetic molecular theory of matter. Kinetic molecular theory of matter. We know that matter is made up of tiny atoms / molecules or ions. We know that matter is made up of atoms, molecules, ions. Full stop. The kinetic molecular theory of matter states that matter is made up of tiny particles. States that matter is made up of tiny particles. These tiny particles are always in constant random motion. These tiny particles are always in constant random motion, colliding with one another and thereby possesses kinetic energy. Yes, colliding with one another possesses kinetic energy, thereby possesses kinetic energy. Let's discuss gases a bit. I'll skip some things. Let's focus on what's important, please. Take that, please. The behavior of gases. Can be determined by some factors, which includes the factors that determine the behavior of a gas includes its pressure, P, its volume, V, and its temperature, T. Alright. This implies that the behavior of any gas can be determined. This implies that the behavior of any gas can be determined by its pressure, volume, or temperature. Full stop. Any scientist proposed laws. This should be like a new paragraph, right? Yeah. Any scientist proposed laws which govern the relationship between these parameters. Proposed relationship between these parameters. Or any scientist proposed relationship which govern these parameters. Proposed laws, right? I'm actually saying this from my mind, right? I'm not actually reading. This was just something that just govern me. What I'm saying is actually here exactly. What I have is just a note, right? So just understand what I'm saying. I'm saying that early science is a proposed law that governs these parameters. This law includes number 1, Boyles law. Number 1, Boyles law states that the volume of a given mass of gas is inversely proportional. States that the volume of a given mass of gas is inversely proportional to its pressure. Provided temperature is kept constant. Full stop. Boys, what does it state? States that the volume of a given mass of gas is inversely proportional to its pressure, provided temperature is kept constant. Full stop. So look at it. Alright, let's express Boyles law mathematically, right? Science is maths, maths is science. Science is math. You just cannot know it. You cannot. But that is so explanation. Listen to this update. For Boyles law, we said volume is inversely proportional to what there? Pressure. How do you write inverse proportionality? How do you write that? So let's say volume. So I'm saying that volume is inversely. That becomes this. For inverse, what do you put there now? 1 all over. It's inverse 1 over towards the pressure. Please. This is how you do inverse variation. Alright, provided temperature is kept constant. Let's use V for volume and P for pressure. It means that V is inversely to pressure P. For proportionality there, how do I eliminate this sign? Put an equal to introduce a constant. I will change this one now. V, change here to equal to and put a constant. That's how you eliminate this sign here. Right? Put an equal to and a constant. So this is now this dot 1 all over P. So I have this. In other words, if I multiply this now, I have that V is equal to K times 1 is K all over P. What then is the expression for the constant? This is all over 1. So cross multiply. K times 1 is K equal to P times V is PV. This is like the relationship for Boyles law. Let's copy down this. And the constant is equal to the product of pressure and volume. You can copy this down, please. Let's be split. Which one should I use now? Alright, take that. If temperature remains constant, Boyles law can also be expressed as P1 V1 is equal to P2 V2. If temperature remains constant, Boyles law can also be expressed as P1 V1 equal to P2 V2. Let's define parameter. Where V1 is equal to the volume at pressure P1 and V2 is equal to the volume at pressure 2, 1.2. Right. We have V1 is equal to the volume of the gas at pressure 1 and V2 is equal to the volume of. Trying to explain Boyles law, I said for Boyles law, P1 V1 is equal to P2 V2. I said V1 means the volume of the gas at P1, that's pressure 1. V2 is equal to the volume of the gas at pressure 2. I said volume can be measured in different units, perhaps in meter cube or centimeter cube or decimeter cube or in liters. I said the relationship between meter cube and liters is that 1 meter cube is 1,000 meter cube. We said for the fact that for Boyles law, for the fact that the relationship between the volume of the gas and pressure is inverse proportionality. What does it mean? It means that as one parameter is increasing, like pressure from 1 to 2, from 2 to 3, the other is decreasing, just like volume from 6 to 3 and from 3 to 2. What does this imply? Look at it from a question. Take that please. Example 1. Example 1. A gas contained in a flask. A gas contained in a flask. Before then, hold on. We just said volume is measured in meter cube, cm cube, dm cube, liter. What about pressure? What are the units for pressure? What are the units for pressure? For pressure, what are the units? ATM, atmosphere. That's ATM. What else? Pascal. What else? Newton per meter squared. What else? Millimeter what there? Mercury. These are like the 4 units for pressure, right? So pressure in terms of ATM, that's atmosphere. PA, that's Pascal. Newton per meter squared. Then please take note, please. Take note, please. Standard pressure, because it's supposed to say use STP. STP means standard pressure and temperature. Take note, please. Standard pressure is 360 millimeters mercury for pressure. Standard pressure, that's for this one here. Standard pressure for this one here. In terms of atmosphere, standard pressure is 101,325 atmosphere. Right. One more thing. Pressure can be measured in terms of bar. Right. Take note that 1 Pascal is the same as saying 1 Newton per meter squared. So Newton per meter squared and Pascal are exactly the same thing. Don't forget it. Right? Pascal and Newton per meter squared are the same thing. They mean the same thing. Alright. Having said so, the 36 and the 760. In that it should be 760. Yeah. The 760. Yeah. Will be nice relationship. 1 bar is equal to 10 to the power 5 Newton per meter squared. So note these things. Note that in case of conversion. Note them. Example. A gas contained in a flask. A gas contained in a flask 500 milliliter. That's 500 ml. 500 milliliter capacity. 500 ml capacity. Was allowed to expand into another flask. Was allowed to expand into another flask of volume. Was allowed to expand into another flask of volume. Now hang on. Look at this one. They gave me a volume first of 500 milliliter, and they say it's expanding into a certain volume. This certain volume, should it be bigger than 500 or smaller than 500? Huh? Bigger or smaller? Why bigger? Very simple. It's expanding. Should go come out there. Bigger. Yes. Alright. So was allowed to expand into another flask of volume 600 milliliters. So why am I showing these things? Some questions could be wrong. So at this point, get to the point where you can read a question and be like, this is not something so, this is wrong. If something is actually expanding, it's getting bigger. So hence, if they give me a volume and they say expand into 450, it doesn't make any sense. Because you cannot expand to a smaller thing. No, it doesn't make sense. Alright. A volume of 600 milliliters connected to a valve. Connected to a valve and at the same temperature. Right? Connected to a valve and at the same temperature. Full stop. Of course, it makes sense. For Boyles' law, temperature is what? Kept constant. Makes sense. A valve and at the same temperature. Full stop. If the final pressure of the gas, is 1.01 times 10 to the power 5 PA, that's Pascal. If the final pressure of the gas is 1.01 times 10 to the power 5 Pascal, comma, when the valve is open, comma, what was the pressure of the gas? What was the pressure of the gas in the 500 milliliter flask? What was the pressure of the gas in the 500 milliliter gas flask, please? 500 milliliter flask, full stop. The volume of the valve is negligible. The volume of the valve is negligible. Alright. Task 1. List out your given parameters. So look at this. Alright. Check your question, please, one more time. Right, so the first one given there is what? Saying a gas contained in a flask of what? 500 milliliter. Which parameter is that? V1. Of course. When you see liter, what comes to mind there? Volume. I've said so before. So when you now see ml, means milliliter, it's still volume. So I'm giving V1 as being equal to what there? 500 milliliter. What next there? So it's allowed to expand into another flask of 600. So I'm giving V2 as being equal to 600 milliliter. I have this one there. Next up, say connected through a valve and at the same temperature. Of course, for Boyles' law, temperature is constant, so it makes sense. Proceed. It says if the final pressure of the gas is this, please, this value here now. Is it? See, my first volume was V1. My second volume was V2. This pressure you're giving here, is it P1 or P2? Huh? From the question, the first volume I saw there was V1, no problem. The second one there was V2, no problem. Now from there I'm seeing my first pressure. That's what I have here. Should it be P1 or P2? P2. Any contrary opinion? No, feel free. If you think it's P1, you feel it's P1. Is P2, let me say it down. Is it gift? Why is it P2? In your question there, did you see final pressure there? Yeah? Why is it P2? You say because final pressure. Did you see final pressure in the equation there? Yes. You saw final pressure there? Yes. Oh, okay. I should have put that thing. I should have put it. Now listen. Let's assume there was no final pressure there. What if the question has said, if the pressure of the gas is this? Let's assume there was no final there. Would it have been P1 or P2? Let's assume the final there was not there. Would it have been P1 now or P2? It's P2 because it's a final, no problem. But let's not assume that there was no final there in that question. Would it have still been P2 or P1? P2. Why P2? Why is it P2? That's just it. Don't you? The hints there's in the last question. See the question. The question says fine was there. What was the pressure of the gas in the what? 500. What was the pressure in the 500? You're asking for this one. That's like the key concept there. So you're going to verb open and close it. You're completely over down. Online the question there. What was the pressure in the 500? The 500 there was what? V1. So the concept there, P1. And I said, what's V1? V1 is what? The volume at what? P1. That's how we define it. That's the concept. So hence, P1 or P2 per se. P2 is equal to 1.01 times 10 to the power 5 Pascal. Question. For this now, I gave you relationship before for meter cube and liter. In this question, you have to convert, yes or no? For this question, you have to convert, yes or no? Huh? Yes or no? The reason for conversion, I've said before, the reason why we convert parameters is to ensure uniformity of given parametric units. In other words, if the parameters are in the same unit, no need for conversion. That's all. This one here is in milliliter. V2 is in milliliter. They are the same thing. No need for conversion. That's it. So let's assume this one now was in milliliter and this one now in meter cube. That's when you convert them. Alright. So P1 is equal to unknown. That was the pressure at P1. From here now, you see from Boyles law, don't get that? P1 V1 is equal to P2 V2. Alright. I'm looking for P1. So make P1 subject of the formula. How do you do that? Divide here by V1, divide here by V1, such that V1 cancels V1. I have that P1 is equal to P2 V2 over what there? V1 equal to, what's P2? 1.01 times, that's what there? 5. What's V2? 600. What's V1? 500. Please punch this, give me total value. Punch this, give me total value, please. Now please, mind you, when you're punching this, please, mind you punch this times this equal to, get your answer first before divided by 500. So what do you get? What do you get? From here, this cancels this and this goes up. This and gives you what there? Huh? What do you get? Talk to me, what do you get? 0, Abi? Alright. Okay. So what's the unit here? What's the unit here? That's P1. Alright, so I'm having that value there. Huh? If you want to know, express this in index form. What do you have? What do you have? What will it be? That will be equal to what there? Start from here. 1.2. Go this way now. 1, 2, 3, 4, 5. So 1.212 times by what there? 5. Please, here's the thing, please. Here's the thing. Right? Okay. So I have this one. Which of them, please? Do you get this one here? You get this? You pick a calculator there. And you pick a calculator now. Calculator, press this times this. You have an answer. Divided by 500, you have this. You pick a calculator. So much. This one here. So I'm saying this. This is your value here. Now I want to express this in this form. Look at this form here. This form is actually point this. Right? So how do you get it in terms of 1 point something? How do you get it in something point something? What do you do there? If I have this value here, I want to get it like that, 1.01. So I want to get 1 point. I want to put points here. From here now, move towards the end. Count how many times you're moving. I'm moving 1, 2, 3, 4, and 5. That's about 5. So it becomes 1.212 times 2 by 5. That's it. That's the concept. Alright, next up is example 2. 375 cm cube, example 2. 375 cm cube of a gas. 375 cm cube of a gas has a pressure of 770 millimeter mercury. That's mmHg. 375 cm cube of a gas has a pressure of 770 mmHg. That's millimeter mercury. Full stop. Find the volume. Find the volume if the pressure is reduced. Find the volume if the pressure is reduced to 750 millimeter mercury. Find the volume if the pressure is reduced to 750 millimeter mercury. Full stop. Alright. So case 1, list out the given parameters. What are you giving there? You're giving the first volume, that V1. So I'm giving V1 as 375 cm cube. Alright, said 375 cm cube of a gas has a pressure of, so you're giving the pressure at this point, that's P1. Pressure at this point, that's P1, has been equal to what there? 770 millimeter mercury. I have this. It said find the volume if the pressure is reduced. So my second pressure there, P2, is about 750 millimeters mercury. So I say find the volume at this point. P2 is unknown. Alright. From Boyles law, what do we know? How that P1 V1 is equal to P2 V2. I'm about to find V2. To make V2 subject of the formula, how? Divided by V2 divided by V2. These cancel this. So I have that V2 is equal to P1 V1 over P2. Impute value. What's P1? Of course, in this case now, I'm not converting the same unit now, so I'm not converting. P1 is this 770. V1 is this 375. All over P2 is this 750. Alright. This P2 now. So P2 equals what the word there? P1, P1 over P2. Right? Correct. Give me this whole answer. So what do you get here?
2 is 700.
You get what there? Let me find out somebody else.
3 is
385. That's V2. Please, what will be your unit for V2? What's the unit? To follow the first one, CMQ. Contour now. CMQ. So observe, as pressure reduced from 770 to 750, what will the volume? Increased from 375 to what there? 385 increase. And that's what we say. As pressure is reducing, the value has reduced. The value of volume has increased. And that's what is called inverse proportionality. Questions? If you have P1 V1 equal to P2 V2, what's the question there? The question says find the volume if the pressure is reduced to this. So here's my first volume, here's my first pressure. They gave me my second pressure and say find the volume at this pressure, right? Right, so I'm looking for the volume at this pressure now. From Boyles' law, I have this formula here. If I have this per se, how do you get V2? What do you get? How do you get V2? So now becomes mathematics, no longer chemistry, now mathematics. How do you get V2 here? What do you do? Make V2 valuable. How? Make V2 subject of the formula. How? The V2 is attached to P2. So I'll look for a way to eliminate P2. And how do I do that? I'll do that by dividing both sides by what is attached to V2. In this question here, what's attached to V2 here? That's P2. So I'll divide here by P2. I'll divide here by P2. In this case now, P2 here will now cancel P2. I'm now doing that V2 is equal to what there? P1 V1 over P2. And that's the concept of using. It's not like a mathematical approach. Huh? Let's say you want to convert. What do you do? Huh? So look up. Very fast, look up. Let's say they gave me V1 as equal to, let's say, 2 meter cube, and V2 as, let's say, 0.3 meters. Fine. Now 2 different volumes. I want to convert. What do I do? How do you convert? Huh? No, I shouldn't be doing this. This is not wire class. I shouldn't be doing this. Shouldn't be doing this. This is not wire class. I shouldn't be doing this. But whichever way, let me do it. Look at this. So I'll say to one and off. Listen. Conversion is a two-step process. Conversion is a two-step process. What's the first step? The first step is to get a relationship between the parameters you're converting. For instance, what I have here is meter cube and liters. So if either I choose to convert V1 from meter cube to liter, or convert V2 from liter to what there? Meter cube. So hence, the two parameters I'm converting are what? Meter cube and liter. So question, what's the relationship between meter cube and liters? I know that 1 meter cube is equal to what there? 1000 liters. Case 1, get the relationship between the parameters to convert it, that's all. Case 2 now, you now ask yourself, which do you want to convert? Do I convert this one to meter cube, also the liter, which of them? Let's assume this one here. Let's assume I want to convert this one here. So I want to convert it to liters. What do I do? Look up, what do I do? Now this side works. This value is 0.3 under liters. So I'll come here. Here's meter cube. Here's liters. Equal to, under the liters I'll put 0.3 meter. What's the value of meter cube? I don't know. Call it x. That's what you do. Case 1, get their relationship. Case 2, bring them in. 0.3 under liters. What's the value in meter cube? I don't know. At this point now, cross multiply. So it becomes, when you cross multiply per se, you will ignore the units, just take the values, that's the numbers. This times this, that gives you 0.3 times 1 is equal to this times this, 1000x. Because this times x gives you this times 1 is itself equal to this times this is 1000x. How do you get x? Divide by 1000. Divide by 1000. This cancels this. So x is now equal to this. What do you get here? 2.567 times 2 by 1 there. Cannot be 5. Check your calculator now, you don't guess it. What do you have there? 0.3 times this. How does it give 2.56? Back is what do you get? 0.3. 3 zeros. And what do you get there? This. That's what happens. That's the concept. This is correct. Let's see the second law there called Charles Law. Charles Law. Alright, Charles Law please. Charles Law states that the volume of a given mass of gas is directly proportional. The volume of a given mass of gas is directly proportional to its temperature. Provided pressure is kept constant. The volume of a given mass of gas is directly proportional to its temperature, provided pressure is kept constant. So here's your mathematical expression of Charles' law. It means that volume is directly proportional to what there? Temperature. And so let the concept for Boyles' law, temperature is constant. For Charles' law, pressure is constant. You can see that, right? So of course, I said to take off your proportionality sign. What do you do now? Put an equal to and constant, and of course T. What's K here? K is equal to what there? V over T. I'm having this. So K is equal to V over T. Alright, so of course, if pressure remains constant here, it means that V1 over T1 is equal to what then? V2 over T2. This is the expression for Charles law. For Boyles law, P1 V1 equal to P2 V2. For Boyles law, temperature is constant. For Charles law, V1 over T1 is equal to V2 over T2. At this point, pressure is kept constant. Alright? It's kept constant. Let's add up things. When we did Boyles law, we discussed about volume in each several SI units. We also talked about pressure. So in this case now, the same concept works here. So volume in either meter cube or dm cube or liters or cm cube as case may be. What about temperature? When it comes to temperature, what are the various units of temperature? Huh? In what? Kelvin. What again there? Degrees Celsius. What again there? Fahrenheit. Right. So these are like your various units for temperature, either in Kelvin or in Celsius, degrees Celsius, or in Fahrenheit. Now listen to this. For Jamb's sake, listen up. I said something, listen. I said when it comes to volume, if they are the same thing, leave it, don't convert. Whether they are both in liters or in cm, don't convert. When it comes to pressure, if they are the same thing, don't convert. Whether millimeter mercury or bar or pascal. When it comes to temperature, please listen. Always convert. Please. Always convert. For temperature, it's acceptable that the unit for temperature should be what? Kelvin. Please. So the only way you're actually converting there is what? Is temperature. Don't forget it. Always convert temperature. You can add it there, please. Always convert temperature to Kelvin. Always convert temperature to Kelvin. For Jamb's sake, you'll be given temperature as either Kelvin or degrees Celsius. Fahrenheit is not really used. In fact, I've never seen it before. So you can for both Fahrenheit. What's the relationship between Kelvin and degrees Celsius? Note that Kelvin, the value of a Kelvin, K, is equal to the value of degrees Celsius plus 273. That's the thing. If I'm given a particular value in Celsius, I want to convert to Kelvin. What do I do now? Add 273, and that's all. For instance, let's say I have 25 degrees Celsius. Convert this to something in Kelvin. What do I do? The value in Kelvin becomes what there? This one here, 25 plus what there? 273. Sum is what gets now? 892 Kelvin. That's value. So this is how we convert from degrees Celsius to Kelvin. Add 273, that's all. Example. What example have we done? Example, yes. Is it constant? Yes. It's constant. 273. Example. Add 17 degrees Celsius. Add 17 degrees Celsius, comma. Add 17 degrees Celsius, comma. A sample of hydrogen gas. A sample of hydrogen gas. A sample of hydrogen gas occupies 125 cm3. Occupies 125 cm3. Full stop. No problem. What will be the volume? What will be the volume at 100 degrees Celsius? What will be the volume at 100 degrees Celsius if pressure remains constant? if pressure remains constant. Please get these thoughts in your head. There are too many formulas. But get them in your head, right? Yeah, try to. So for Charles Law, pressure is constant. Okay. Alright. Solution please. Case 1. List out your given parameters. What am I given? So the first thing there is what? 17 degrees Celsius. I'm giving T1 as being equal to 17 degrees Celsius. Occupies, they give me V1. So I'm giving V1 as being equal to what there? 125 cm cubed. Next up, I'm giving second temperature T2 as what? 100 degrees Celsius. Alright, I'm asked to find the volume, that's V2. Now look at it. For this case, am I converting? Yes or no? Huh? Yes. Now listen. I said we only convert parameters when they are not of the same unit. In this case now, they are of the same unit. So am I converting? Yes. Huh? Yes. The idea of converting is to ensure uniformity of given parametric units. They should be the same thing. When they are the same thing, you don't convert. Temperature, yeah, that's what I said. You don't convert. So in this case, am I converting this? Am I converting? Yes, I'm converting. Why? I was trying to confuse you. Yes, I said before, please. When it comes to this topic, the only thing you must convert is what there? Temperature per second. Right. Convert this number to Kelvin, it becomes what there? 17 plus what there? 273. This gives you 10, 8, 9, 290 Kelvin equal to 100. Add what there? 273. It gives you what here now? 373 Kelvin. So I'm looking for V2. So V2 is equal to unknown. From here now, of course, from Charles Law, you call it from Charles Law or from Charles' Law? Huh? We have that word there. V1 over T1 is equal to what there? V2 over T2. I'm asked to find V2. How do you find V2? Case 1, cross multiply. This times this times this. So V2 T1 having V2 T1 is equal to V1 T2. V1 T2. Get T2. What do you do here now? Divide by T1. Divide by T1. This cancels this. Means that V2 is equal to V1 T2 over T1. Input values. What's V1? This value here. 125 into T2. This 373 all over T1 290. Please give me final answer. What do you get? 1 what? 77 what? What's the answer? 775. 775 is what? 78. 775 is 78. That's approximation. Jamb will give you 77 and 78. Choose 77, you're wrong. Please. No, you can't say 77. Approximate it because of there. 78. So look up. Listen. Let's end this concept. Let's end this concept. We said for Boyles' law, the relationship was what there? Inverse proportionality. What does it mean? As one is what? Increasing. The other one is what there? Reducing. For Charles' law is what there? Direct proportionality. What does it mean? As one is what? Increasing. The other one is what there? Increasing. You can see. As T1 increased from 290 to 373, V1 also did what there? Also increased from what? 125 to what there? 1. So it's is mathematics. That's the fun of maths. Not the maths, you just manipulate it. Alright.